Hello students. So let's continue with the synchronization concept. So in the previous session we have gone with the synchronization clocks, right? So there we have discussed about the types of the synchronization algorithms, where we have a physical clock algorithm and a logical clock algorithm, mutual exclusion, and the elections algorithm. So as we have done with the first part, we are moving to the second part, that is the logical clock algorithms. See here, in the logical clock algorithm, the only thing is we have to maintain the relationship between a number of nodes, right? So when a process is about to start, which process? I mean, when a process is going to start, at that moment we are going to encounter with one variable, and that variable will be the resultant of that clock structure. So if one process 2 is there, that will be having its own counter variable and it will be incremented at that moment. So that is what will be happening in the logical clock structure. So let us start with this first of all. See, logical clocks are nothing but the which will be taken place when we are going to trigger few events over there. So if an event occurs, immediately the synchronization clock approach to be highlighted over there, right? So here we have the structure will be like this. See, we have n number of systems in the distributed environment. If we are taking this system will be highlighted with the process 1. Let us go. Now when it is utilizing with the process 1, somewhere it has process 15. So it need this process 15 to be executed, right, from this system. Now how it is possible? So with one procedural call, that's it. We know this concept, RPC concept. Now we are going to call that RPC method call, so that this 15 method will be accepted and it will be giving the result. Now when this P1 is executing, the counter will be 1. When it has been stopped and when this was highlighted, its counter will be highlighted to 1. Got this? So this structure will be maintained in the logical clocks. Now what is this happen before relationship is nothing but when a process starts, process B is executing. See, process A executed first, process B is about to execute from A. So this is nothing but happen before relationship, that is nothing but A must be executed before B. Then only that will be the successful execution part. Got this? Now the second procedure is also, see, A is executing, so we call this as a process 1. From A I am calling B, so process 2 will be highlighted over there. So the extension of this will be shown like this, right? And all the time remember that the timestamp of A must be lesser than timestamp of B. Yes or no? Because A is starting first, with A we are starting B. See, obviously if it is started at 2 p.m, it must start at after 2 p.m. itself, right? So that is what the timestamp must be given with this condition. So timestamp of A must be less than timestamp of B. Now there are 3 types of relationships. The first one is transitive, second is casually, and third one is a concurrent. See, transitive is nothing but if one process is executing A and we are moving to B, and from B to C if I am moving, so that indicates that I am directly moving from A to C, right? So that is what is the transitive. If I say A equal to 5 and if I say A equal to B, now B equal to C means, so that is nothing but B is 5 and A is also equal to C, that is nothing but transitive. A equal to B, B equal to C, and A equal to C will be the final answer, right? So this is a transitive relationship. Now casualty. So casualty order is nothing but when an event occurs. See, event A is started with its execution. Now when it started with its execution, casually if it is calling so and so process to be highlighted, so this is under casually order. See, from A to B, and B is about to start with C, and C is about to start with A back. So like this, if you are having a sequence of process execution, so that is under the casual ordering. Now the last one is a concurrent. See, concurrent is nothing but when A starts, immediately B also starts. So that indicates that A and B both are executing parallelly, right? So A started with P1, at the same time B started with P2. That indicates that A and B are parallelly executing with each other. So that is what a concurrent event processing, right? Now we are entering into the algorithm of logical clock. See, the algorithm is taken into this advancement also. So this is the first basic version and its advancement will be with the vectors. Now what is the basic algorithm? See, coming to the basic algorithm, every process, whatever we are executing in one application, so when we are executing that process will be allocated with a one counter variable. Now, when I call that particular process, immediately counter variable will be incremented to 1. Right. So like that, all the sender and receiving processing will be given with the counter variable. Like how many times you have called that process will be the result of that, and that will be taken as a timestamp. See, counter is assigned as the event as a timestamp. Means the counter variable is indirectly posing that value to the timestamp. That's it. So with this timestamp, we are going to play like in the vectors also. So let us see how it will be. So this is about the vectors clock. See, coming to its highlights, it will be having all the properties whatever we have just discussed, that is transitive, casually ordered and concurrent. So all the properties will be available in this. Along with that, we will be maintained with a one vector. So vector is nothing but, see, there are three processes, orange, green and purple. There are three lines, three processes. So when we are running these three processes, we will maintain all the process data in one vector, in the one vector format, that is 0, 0, 0. Let us assume initial value says 0, 0, 0. So whole three processes will be given under one vector, and this vector will be playing as like this. See here, when we have started, all the values of all the processes are 0, 0, 0, 0. Right. Process 1 is the first 0, process 2 is the second 0, process 3 is the third 0. Right. Now when I have started an event with A, so immediately my process 1 must be given the counter value as 1. Right. So when I have given the another one, the counter value should be 2. Right. So from A, see, from A I am calling, see, process 2 is calling process 1. So immediately my counter value will become 2. Right. So new event occurred here, so that process value will be updated to 3. Right. So like this, if we have started executing whole process, now process 2 called itself, and the value will be 1 over there. So like this, if we start building all the values like this, so how many timestamps will be taken care, and what will be the maximum value of all the vectors will be taken as a final result. Yeah. So after having all the counters value with us, finally the values which are maximum at counter 1, that is P1, will be taken as a final result. And what is the maximum thing in the process 2 is 4, we will be taking that. And what is the maximum value in the process 3, that is 3, will be taken. So the final counter timestamp for that particular whole application will be taken as 543. So this is the final result which we are going to give with the Lamport's vector clock illustration algorithm. Right? So this is all about the logical clock synchronization. If you have any doubts in the first two algorithms, just feel free to contact anytime. Thank you for listening.